Okay, so here's the video for section 2.1. What I have in the boxes are just some definitions straight from the book. So when a function is increasing on a certain interval, that's happening because it is rising as x goes from left to right throughout the interval. So that means whenever you'd go from a value x sub 1 to x sub 2, where x sub 2 is greater, the function does the same thing. The function value at x sub 2 is also greater. And if the function is increasing at a point, that means the function is increasing at some interval that it is around that point or contains that point. So in other words, if this is c and I know my function is increasing, that means that I could create a little neighborhood around c, and it's increasing in that little neighborhood around c. Decreasing is the exact opposite. As your x values get larger, your function values get smaller. And you're decreasing at a point if the function is decreasing in a little interval around that point c. So what we're going to be interested in is the places where functions change from increasing to decreasing or vice versa. And those points are going to be called relative extreme points. And the extremum is the singular version of extrema. So we're looking for a place where our graph changes from increasing to decreasing or the other way around. Relative maximum is a place where my function changes from being increasing to being decreasing. So at x equals a, we would have a relative maximum. A relative minimum changes from decreasing to increasing. So at x equals a, we have a relative minimum here. So relative is important to understand that you could have multiple relatives. So if I draw a graph that looks like this, I have a relative maximum here, a relative minimum here, another relative maximum, another relative minimum, and yet another relative maximum. So there are multiple places where you can have this occur in the course of drawing your function. And the way I like to think about it is, if you are standing on the graph at this point and you look left and you look right, if you're the highest value in a little neighborhood around yourself, then you're a relative maximum. And if you're standing here and you look left and look right and you realize that the points around you are greater height than you are, again, we're measuring height. That's what we are the maximum of or the minimum of. Relatively, you're the minimum height in the little neighborhood around you. So relatively just means it's a turnaround point going from one direction to the other, and there could be a multiple of them. Absolute maximum and minimum, that's a totally different thing. To be an absolute maximum or absolute minimum, you have to have the largest value that the function assumes on its entire domain, or the smallest value that a function assumes on its domain. Meaning, if I look at this minimum here that was relative, it is not absolute because both of these arrows indicate that the function is going to keep going down and down and down and down and down, and it will never reach an absolute minimum. So there would be no absolute minimum on this graph. If I change this a little bit to make this tallest, it would have an absolute maximum. The highest point that this graph achieves is whatever this y value is. It is an absolute maximum because there are no larger values of the function on the entire domain because this keeps going down. So there might not always be an absolute maximum or an absolute minimum, but there will be if you take away the arrows. If you close the interval and you only talk about a domain that goes from 0 to whatever this value is here, let's say it's 5. We'll call it 5. If you say that's how I'm limiting my domain, then you do have an absolute maximum right here and you have an absolute minimum right here. because your function doesn't go any higher than the value of 5 or lower than value of 1. So on a closed interval, you will be able to find absolute maxes and mins. If you don't have a closed interval because you have these arrows indicating the domain is all real numbers, then you might not be able to find one. This is a relative max as well as an absolute max. This is a relative min as well as an absolute min. But sometimes your absolute min, which would be this value right here, the y value is 2, so the absolute minimum value is 2, that is not a relative min because endpoints cannot be relative mins. If you are imagine standing at this point, you can't look left. And so you're not at a turnaround point, you are just at an absolute min, not a relative. This would be a relative min, but not an absolute min. This would be a relative max, but not an absolute max. So they say no max value. I'm assuming that they meant to put an arrow there to indicate, since they didn't put a dot, then you assume that an arrow would be here. They had a dot here. This is an endpoint, so the domain was from 0 and then it went on out, which means no maximum value because it's just going to continue rising. So big difference between absolute and relative. You just want to make sure that you understand the distinction between the two. So if I wanted to draw a graph here for this top part, draw a graph that's increasing, we know there's two ways to increase. To increase only means that as my x values get larger, so do my y values. So if I was increasing on this interval, then because this x value, maybe that's 2, is smaller than this x value, this y value has to be smaller than that y value. So if I'm going to go from here to here with my function, I'm going to be increasing. But the question is, increasing at an increasing rate, what does that mean? Well, that means that if I went from this point to this point in a straight line, I'd be increasing at a constant rate. So every time I went to the right one, I went up the same amount. To increase at an increasing rate would have to look like this. My graph, if I look at the tangent lines, are getting steeper and steeper and steeper. So increasing at an increasing rate looks like that kind of a curve. Where increasing at a decreasing rate, I still have to be going up. As I go to the right, I have to be going up. But I'm going to do it like this, so that my tangent lines are getting less and less and less steep. Remember, the tangent lines are measuring the rate at which you're increasing. And these tangent lines are getting less and less steep. That's a decreasing rate. Decreasing means that as I go from one x value to a larger one, my y values actually get smaller. So if this was 3 and this was 4, my function value at 2 is 3, but my function value at my function value at 2 is 4, but my function value at 5 is 3. So my y values are getting smaller. This would be at a constant rate if I did a line. But to decrease at an increasing rate, I need the slopes of my tangent lines to get more and more negative. So to get more and more negative, it would look like this. Because my tangent lines would be sort of have a negative slope, but they'd be getting more and more negative as I went. So my tangent line slope might be, negative 1/2, and then it might be negative 1, and then it might be negative 2, decreasing at an increasing rate. So decreasing at a decreasing rate, then by default has to be this. My tangent lines might be negative 5, and then negative 4, and then negative 3. So the fact that I can increase at different rates, and that changes the way my graph curves, And the same thing with decreasing means we have a new concept that we're going to talk about, which is concavity. So concavity at a certain point means that if you look around that point, that's what they mean by open interval. So you look around that point on the x-axis. If the graph of the function lies above all of its tangent lines, then we are going to be concave up. So if you drew all the tangent lines to this, they would all lie below the graph. That is what it means to be concave up. So concave up would be this graph, but it would also be this graph. If you looked at that graph and you drew all its tangent lines, they're all underneath the graph. So both of these are concave up. Concave down then is the opposite. So concave down, you see how when I drew these tangent lines, they were all on top of the curve. Same with these tangent lines. So this is concave down. Concave down could look like that, or concave down could look like that. So an easier way to think about it to me is if you imagine that it starts raining, sort of silly, but it starts raining. Concave up graphs would hold that rain. Concave down graphs would shed that rain. That would just, the rain would flow off it. So an umbrella is concave down. If you turn your umbrella over, it's concave up and it holds the water. So that's just an easier way to think about it. So a new idea now is an inflection point. If we happen to have a place where our umbrella is turned upside down, or it's the way it should be, and it changes, so it changes from concave up to concave down, we're going to give that point a new name. It's going to be called an inflection point. And it could be that it went from up to down or down to up. It doesn't matter. It's still an inflection point. So we have relative mins, relative max, and inflection now. That there's something the same about all three of those things. They are a place where your graph changes. But the change is different. A relative min, the direction changes from decreasing to increasing. Relative max, the direction changes from increasing to decreasing. And an inflection point, concavity changes. So concavity changes either from up to down or down to up. They're both inflection. So there isn't a distinction like there is with relative min and max. So these are new words that are going to help us as we try to graph some functions that we're going to take a look at. So it's just some things we already know about graphs. We know x-intercepts are the points where our graph crosses the x-axis. Y-intercepts, points where our graph crosses the y-axis. Asymptotes that you learned in 22, you can have horizontal asymptotes or vertical. Vertical asymptotes are domain, they occur at domain issues. So they would occur if you had a function over another function and x is not allowed to be 2, then you would have a vertical asymptote at x equals 2. They don't occur if you have a function on top and a function on the bottom and there's a common factor. That's not going to give you an asymptote. Remember, this would give you a hole because we talked about how to divide out that factor and realize that that would not be an asymptote. So you can't say that an asymptote always occurs when you have an x in the denominator. But when things are simplified and you've divided out all your common factors, then whatever's left in the bottom will cause a vertical asymptote. Horizontal asymptotes are the end behavior of our graph. So if there's a value that x gets larger and larger and larger and that y value approaches a certain value, way at the end, either as x is large or as x is really, really small, then we will have a horizontal asymptote. But one thing that you may or may not know is that just because you have a horizontal asymptote, it doesn't mean your graph can't do this. vertical asymptotes you cannot cross. So that's a red line, you cannot cross it. Horizontal asymptotes can be crossed. They can be crossed any number of times, but if this is a horizontal asymptote, in the end, my graph is going to come up and approach it. So as my x values get more and more like infinity, more and more like infinity, the graph is going to approach it. It doesn't mean that you won't cross it. So if there's a horizontal asymptote of y equals 3, it doesn't mean the function will never take on the value 3. It just means that as x gets really, really big, that's going to be a limiting value for the function. So if you want to describe a graph, there's some things that you can do to describe it. And you have a graphing calculator. So, you know, I'm going to want you to make these kind of comments about your graph and not just draw me a picture. Because drawing me a picture would be just taking your graphing calculator and sticking it down and drawing what you see. So I want you to be able to mention intervals where the function is increasing or decreasing. If there's any relative maximum points or relative minimum points. Maximum or minimum values, these would be absolute. So if there are any values that you don't get larger than or smaller than, they would be absolute. Concavity in your graph, where is it a concave up, where is it concave down? Are there any inflection points? Your intercepts, any undefined points, so they would be either holes or asymptotes, and then asymptotes leads down to here because maybe you have a y asymptote also. I mean a horizontal asymptote also. So what it would look like with this graph, if we look at number 1, this function is increasing here. So it's increasing up until the number -1 on the x-axis. But then it also starts increasing again at 3. So you would write it's increasing from -infinity to 1, and then again from 3 on out to infinity. So because there's no dot here ending it, we're assuming an arrow. So decreasing is in between those two, in between 1 and 3. Now we're measuring these on the x-axis. So these, sorry, -1. These should be negative ones. It was in -infinity to -1 and 3 to infinity. And that means that it looks like I have a relative maximum and a relative minimum because there was a place that it went from increasing to decreasing. That gives me a relative max at -1, 1, 2, 3, 4, 5, -1, 5. And a relative min at 3, -2. In terms of absolute, there's no absolute. No absolute min, no absolute max, because it keeps going up here and down there. Concave up and concave down. So this is a little trickier because you've got to figure out where that changes, but they put a little dot out here to help you. They actually put the change in concavity and they marked it right here. So concave down is this part of the function. Concave down would be from -infinity up to 1. And concave up would be from 1 out to infinity. And the inflection point is that change. So I would call it 1 and maybe 1/2. Looks like the y value there is 1/2. X-intercepts. It looks like it's crossing here, here, and here. So we'd have to approximate the x-intercepts. We'll say negative, I don't know, 2 1/3, 0, 1 1/3, 0, and 4 1/2. Can't be really much more specific than that. Y-intercept. because this is a function, there's only going to be one y-intercept, and it looks like it's hitting here around 3 1/3. So 0, 3 1/3. There are no undefined points. That was 4. There are no undefined points because there's no holes, there's no asymptotes. And there are no asymptotes because this is heading up to infinity and this is heading down to infinity. There are no boundaries that are blocking its rise or its fall. So there's no horizontal asymptotes, and since there were no undefined points, there's no vertical asymptotes. So that's what we're heading toward discussing, you know, sort of building a little bit on what you already know about graphing from Math 22 and using the idea of the derivative that is going to help us find these places where the graph turns around, because we're going to know that that's happening because the tangent lines are horizontal.